No, this one.
Good afternoon and welcome to the only news channel dedicated to bringing you live footage of Sir Isaac Newton. I'm your host, Jay Bundren, and welcome to Newton Watch. We begin today with some breaking news. We'll go to our on-the-scene reporter, Vance, who has the rare opportunity of sighting Newton here in central PA. Vance, what's going on?
As you can see, Sir Isaac Newton is having a mental breakdown over the different electronics throughout the physics lab here at Dickinson College. Newton seems most perplexed by our radio and the accompanying sound as he turned on the system. Something many of us know how to be explained by the electromagnetic radiation, a main theory contribution to our understanding of light and quantum mechanics. This phenomenon can be explained as a different color and spectrum of light as we see. And even though we can't, William Herschel, an astronomer working at the Society of London, published a paper explaining the existence of IR radiation. It served as a galvanized the discussion over the existence of all the kind of radiation. The discovery of many forms of radiation we know today, including radio wave, are due in part to quantum mechanical experiments.
As I was saying, the different colors of light we see previously unexplainable using Newtonian physics. But thanks to Herschel and others like Marie and Pierre Curie, we've been able to explain the behavior of light, and now we've developed quantum models to explain these phenomena. The photoelectric effect is one of these models, as scientist Heinrich Hertz discovered in the late 19th century. Hertz was able to observe metals emitting electrons, or photoelectrons, by shining light onto the metal to overcome a certain threshold frequency and dislodge these electrons. These emissions of photoelectrons can be explained in wave functions, where electromagnetic waves are emitted in quantized photons of energy. Now let's check back with our man on the scene to see how he's faring.
So all of this quantum talk has really messed with Newton's head. He couldn't comprehend the quantum mechanics. Let's see if we can find him.
Vance, are you okay?
Hello, I'm Sir Isaac Newton.
And I'm Ernest Rutherford.
Ernest, why is it that when I have a sample of iodine, it sort of loses mass after a week of just sitting there undisturbed?
Oh, Isaac, you dumb rascal. There's a very simple explanation for why your sample is decreased in mass.
Don't belittle me.
You see, I've been studying for quite some time this theory called radioactive decay. An element, can have something called a half-life, which is the time it takes for it to degrade into one of its isotopes. Each element has an isotope with a different half-life. The element can emit what I like to call alpha and beta rays.
This literally makes no sense to me. How can an atom lose mass? And how can an atom emit waves? What you're talking about is absolutely ridiculous.
Let me
Rutherford.
finish, please. So these rays are actually particles. The alpha rays that I've been talking about, you see, they're hydrogen nuclei, and I've been seeing them in my scintillation detector. The beta rays have turned out to be electrons. Vance.
I still have no idea what the Planck you're talking about.
Hey,
How are we doing? How are we doing?
And Newton, how's it going?
Oh, he was just blurting out some psychobabble about physics and whatnot.
I was just explaining radioactive decay.
It seems like this is a constant area of trouble for you.
Anyhow, Newton, your sample of iodine must be the iodine 131 isotope, because it has a half-life of 8 days, which is the time for half of its sample to degrade and to lose an electron and a proton.
When you drop a rock into the water, you know what sound is made?
What?
Clank.
Get him out of here, please.
So your sample has gone through radioactive decay, you see, and it's a quantum phenomenon.
I'm really not interested in hearing this anymore. I'll talk to you guys later.
While we're waiting on Vance, here's a little more about the history of quantum mechanics. So because of the gold foil experiment performed by Ernest Rutherford, we now know that the actual size of an atomic nucleus is less than a billionth of the size of the whole atom. For this reason, if we took all of the atoms that make up every member of the human race and packed them down tight enough so that there was no space in between each of them, the volume of the space that those atoms would take up is about the size of a cube of sugar. What about an easier concept for him to grasp? Take a race car, for example. The faster the car travels, the more dense around the air the car becomes. The more dense the air becomes, the more power the car will need in order to push past the air with a greater speed. The more power a race car has, the heavier it will be, and again will be slowed by the air. This is a problem all car manufacturers face today. How can we make our car faster, lighter, and more energy efficient without costing millions of dollars? Similarly, in quantum mechanics, Albert Einstein theorized that there is a finite speed a particle can travel. Einstein said that a particle can travel no faster than the speed of light in a vacuum, which is 300,000 kilometers a second, because the more massive a particle becomes, the greater the energy is required to move it. Interestingly, prior to Einstein's theory of relativity, physicists managed to define the two states of light from a simple experiment. The dual slit experiment proved to be important for multiple reasons. We were able to establish the observer effect, that is, when light is shined through a very, very small slit, something interesting happens. It begins to narrow on the other side of the slit until, as the slit is shrunk further, the light begins to spread. The observer effect is as follows. If we look at the back side of the slit where the light is shining, we can make out individual particles. But if we look at the screen being hit by the light, we see light acting as a wave. This is the observer effect. This observer effect changes the way we perceive light. It feeds into the wave-particle duality theory that says that light can act as both a wave and a particle. Well, I think we've all had enough quantum jargon today, and I also think I have to go make sure that Vance is still alive. But the next time an apple falls on Newton's head, we'll be there to track it for you. Thanks for watching Newton Watch.